Graviton preside the conference that will happen next week from Monday to Friday in Principia, for those of you who will still be around. And one of the distinguished organizer and participant since the early days of the conference is Henrik Johansson from the University of Uppsala. So he's Swedish originally, so that's where he did his master. Then he started for the usual postdoc tour to California, and then I don't remember which order, CERN and Saclay, or Saclay and CERN.
Yeah, the latter.
No,
Yes.
Then Saclay, before going back to almost home, I mean, back to Sweden, not quite the same place, back to Uppsala. And I mean, he was one of the first proponents of this correspondence between gravity and gauge theory. He will tell us about. Please.
All right. Thank you very much. It's a pleasure to be here. First time in Sao Paulo and first time in South America. It's wonderful to be here, especially coming from a cold country. Yeah, also great thanks to the fact that you're hosting QCMS Gravity School and Conference. Thanks to Nathan as well for being behind all of this, I assume. Yeah, I guess what I'm going to talk about today is going to be part very low-level stuff, but then I'm going to go into more technical stuff towards the end. Hopefully, most people haven't fallen asleep by then. And some of these things you're also going to see at the school and at the conference next week. All right, so I'm going to talk about scattering gravitons, but also talk about black hole amplitudes, general relativity, and how we think about it in a modern day. But let's start with the old way of thinking of it. We're going back to Einstein. So Einstein, more than, well, I guess 110 years ago, formulated general relativity as a geometric theory of gravity, which replaced Newtonian gravity. It was relativistically invariant or covariant. And his way of thinking about it is that space-time is curved by matter, matter curves space-time, and matter follows geodesics in space-time, at least if they are test bodies. And that's, of course, the way we're taught in textbooks. That's the original geometric way of thinking of GR. But that's also a modern understanding, which I guess many practitioners these days take. And that's just GR is simply your ordinary field theory, but for spin 2. So we know of many field theories, Maxwell theory maybe being the first one. And GR is simply in the same family as those theories, but it describes spin 2 particles. I'm not responsible for the artwork, but yeah, you can imagine what it represents. All right, so let's talk about some of the famous stepping stones after GR was discovered. So pretty much right away, next following year, Schwarzschild, of course, wrote down his famous solution, I guess during the First World War. And this was essentially a spherically symmetric, non-rotating, static solution, which is highly celebrated. Today, we think of it as being a non-rotating, non-charged black hole. And there's some pictures here which are most for artistic purposes. It has some famous singularities. It has one singularity at a finite size and one singularity at the origin. We know, of course, that the first singularity at this finite size, Schwarzschild radius, is actually just a coordinate singularity, but that's the location of the event horizon. And I should also point out that although many people think of black holes as complicated objects, I tend to think of it as kind of simple object because it's a non-dynamical object. It's just sitting there, not doing anything, it's being happy by itself. Why do I make that comment? Well, it's because these days many people try to understand the dynamics of black hole, which is a different story. So that's when you have multiple black holes and they interact with each other, and they might merge and they might do lots of crazy things. And those are really what we're interested in. Today, we're not interested in just black holes sitting doing nothing. Okay, then the next famous solution, at least in the modern context, was the solution or finding gravitational waves. So that was also first year after GR was discovered, and this was by Einstein himself. So he noticed that, well, Maxwell's equations have wave solutions, so surely gravity should also have similar wave solutions. However, he was first skeptical because he noticed that the dipole moment, which sources the electromagnetic waves, this dipole moment actually sourced no gravitational waves. So then it looks like, okay, maybe gravitational waves do not exist. Maybe this analogy with electromagnetism breaks down. But soon he realized that you had to go to the next order. You had to go to the quadrupole moment of the source. And then you could see that, in fact, there are waves, two types of waves, just like in electromagnetism. Usually they're called plus and X wave. Maybe friends of Amplitudes community rather think of them as circular waves, but circular polarized waves. But this is like the traditional way of thinking of it. And yes, I think I have an animation over here. So that's how you should think of it. It's like if you have a circle of masses and a wave goes through it, then the plus wave will squeeze and stretch in the vertical and horizontal direction, whereas this X wave squeezes and stretches in the 45-degree rotated directions. Okay. But what's interesting about history is that there was a long debate about whether gravitational waves actually exist, because soon after Einstein's work, Arthur Eddington found that gravitational waves propagated actually faster than speed of light, and he made a joke that they propagate at the speed of thought. So he think that they're real. But later on, it turned out that people noticed that this was just coordinate artifacts. It's easy to get confused about coordinates in GR, and I guess this was one of those examples. But it still begs the question whether gravitational waves could be fake. Just like the coordinate artifacts were fake, maybe the gravitational waves themselves are fake. What you have to ask is, do they actually carry something physical? Do they carry energy and momentum? And there was some work later by Einstein and Nathan Rosen in 1936, where they were arguing that gravitational waves do not exist, despite Einstein being himself the discoverer of them from a theoretical point of view. But I should say, though, that later on they did eventually revise their work. But it's interesting back and forth in history. And this basically made the physics community quite confused. Although, of course, many physicists were smart and they did realize that they should exist, but there was no real solid argument in favor of their existence. But finally, in 1957, there was this famous conference in Chapel Hill where I think Richard Feynman showed up, not being an expert in the topic, but he was sort of wanted to know what goes on in this field. And he participated there. I think some people said he participated anonymously. I'm not sure if that's correct. But anyhow, there he kind of ended the debate by presenting argument which convinced everybody, and this is known as the sticky bead argument. Let me try to go through it. There, and the conference name was the role of gravitation in physics. So he proposed this sticky bead experiment, which is essentially like a detector, although maybe a bit small. But it's a detector for gravitational waves. The point is that you have a bead, sorry, you have a rod on which there are freely moving beads. They're freely moving, but they're also a bit sticky. So each time they move, they will cause some friction to happen. So essentially, a wave passes through, and the beads will move. And they might move back after the wave has passed or whatever. But the point is that friction happens, so it heats up slightly, and therefore the gravitational wave has delivered energy or dissipated energy to the system. And what's important here, of course, is when the gravitational wave passes, the length of the rod does not change, because the size of the rod is set by atomic forces, nuclear forces, and so on. It's not affected by the gravitational wave. Anyhow, so that's a convincing argument, and basically Feynman was saying, essentially what he was saying here is that you need to look at observables. You need to look at things that you can actually observe rather than talk about, the waves themselves. Okay, so to make a long story short, today we have had this great success in building gravitational wave detectors around the world, starting with LIGO in US, 2 locations in US, later on Virgo in Italy, and then Kagra in Japan. There's also a small one in Germany for scientific tests. And there's plans to build one in India, although I'm not sure exactly what the status is of that. And of course, the reason why we're all here is because 10 years ago, almost exactly 10 years ago, there was this famous event, the first direct gravitational wave detection, which has this name, which is basically the date. It pretty much happened as soon as they turn on the upgraded detector, as far as I understand. And it was also a spectacular event. It was a merger of 2 unexpectedly massive black holes, 36 solar masses, 26 solar masses. And the output was a merged black hole of 62 solar masses. And the mismatch, which is 3 solar masses, was radiated off in the gravitational waves. So that's pretty impressive that gravitational waves can carry the energy of 3 solar masses. And there's also some impressive numbers, such as the strain, which is a dimensionless quantity, but you can translate it to essentially measuring changes of distance less than 1,000 the width of a proton. So it's a very impressive experiment. And 2 years later, of course, we were very happy to welcome these guys to Stockholm, and they were given almost an obvious prize. Everybody expected it, I think. So this was for a decisive contribution to the LIGO detector and observation of gravitational waves. You can also read the Swedish version there. Me being a particle physicist, I kind of like to think of this event as a cartoon diagram, which sort of mimics a Feynman diagram. But of course, basically you have 2 incoming objects. They do something. Then you have 1 outgoing object, and then you have radiation. Of course, this is not the Feynman diagram, because this is a highly non-perturbative event, so it cannot really be done in perturbation theory. But it's a nice picture to have. And I should say that this gravitational radiation that comes out here, this is really a coherent radiation of many, 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 many gravitons, if you want to think in that way. Usually we call it gravitational waves, but if you prefer particle interpretation, you can say it's a bunch of gravitons, lots of them. Okay, so with that event, or even before that, for the real experts, it became very important to predict what theory says. And it's a difficult task, because Einstein's field equations are highly nonlinear. So you have to do some approximations. So there's basically 3 regions that you try to approximate separately using separate methods. So this is essentially the gravitational wave, this is the merger, and then eventually it sort of calms down, which is called ring down. So this in spiral phase, you basically see a sinusoidal wave whose magnitude is slowly increasing, and the frequency is slowly increasing. And this can actually be treated using what's known as post-Newtonian, and even today people use post-Minkowski expansion perturbation theory, so it is an analytical method. Then there is a numerical method which is essentially happening here at the non-perturbative region, and there's essentially no other way to do non-perturbative physics than doing it numerically. And then at the very end you can do perturbation theory again, but then it goes under a separate name, typically called black hole perturbation theory. Okay, and what I'm interested in, many of the people in the audience are interested in, is essentially the in-spiral phase. So here we have in mind that we have two black holes which are orbiting each other, and we can essentially assume that velocity and their mass are related by the virial theorem, especially if they have a circular or close to circular orbit. And that means that in this plot here, which shows the orbital velocity and the distance between the black hole, and bear in mind that this is infinity and this is 1, so this is inverted distance. In this plot, you can see the important region that describes binary systems, essentially this diagonal is related, or inverse distance. But as I said, we have several approximation schemes. So there's the most used one, which is the post-Newtonian approximation, where you start with Newtonian gravity and then you add relativistic corrections systematically, both in velocity and in g. And it basically covers this region here. And the post-Newtonian one instead covers a region where you can have large velocities, but not so strong gravity yet. And then you land in this area here. So they both cover the far distance and slow speed region, but then in this parts here they cover slightly different directions, regions. And I guess up here you probably have to use numerical GR. But what I'm interested in, and many people in the audience here is interested in this region actually, which corresponds to ultra-relativistic scattering, or usually we just call it relativistic scattering, where we think of a system not being bound, but rather that they come from far away, and then they come very close to each other, and then they might change the trajectory, and then they go off to infinity again. And the calculations that typically one does, and I think which were reviewed in the school by Ricardo yesterday and the day before, is that you try to compute something from for example, in this case, you that the two black holes, and you try to compute an effective potential. That is one approach. And here you can then turn this effective potential into an effective Hamiltonian, which roughly looks like this. I'm not going to explain what all details are, and also there's dot, 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 because I couldn't fit it on one line. But it looks something like that. And this is the Newtonian part. You might recognize the Newtonian potential. And then there are corrections. The corrections are both for the momentum of the black hole. So these are basically relativistic corrections. And then there are corrections in Gm over R, which are due to general relativity, or the fact that space-time bends. And these were done in this famous work by Einstein, Infeld, Hoffman, and then later on by Droste and Lorentz. Okay, so what do we really do when we do these calculations? Well, often what we do is that we approximate black holes as being point particles, because we think of it as being very far away from the black hole initially. So we just assume that we have point particles with mass m and large m, little m. Here it's just notation. It doesn't mean that there's a mass difference. And then being a quantum field theory person, I like to think that we quantize the interactions. Of course, you don't have to think of it that way, but I like to think of it that we quantize the interactions, and then we exchange spin 2 bosons between the two black holes. in other words, the graviton. Of course, you can just think of it as being, potential modes in a classical field theory. That's fine as well. But I like the quantum perspective. And then you can compute scattering amplitude, which I said is this process where you have incoming black hole from far away, and then they have a close encounter, and then they go off to infinity again. And it's not really the physical situation, but it allows you to compute effective potentials, because they all still have to interact through an effective potential, and that can be computed that way. And of course, the master of perturbation theory is Richard Feynman again. So he comes back a second time in this talk. And you can just use his tools, which are named after him, Feynman diagrams. And you can just sit down and work out to first order in G how a perturbative graviton is being exchanged, and then you integrate over the appropriate things and figure out what the effective potential are. Here I'm really showing how it works in the post-Minkowski expansion, which is an expansion in Newton's power, in Newton's constant. And then you can work out the second power in Newton's constant, and then you get a little bit more complicated diagrams. But it can just be done systematically in principle, and people have done it to quite high order. I will mention some of those names shortly. Let's compare how this post-Newtonian and post-Minkowskian expansion works. So essentially, these are in some sense orthogonal expansions, but they cover similar regions. So the post-Minkowskian, let's start with that one. That's exact in velocity. So it includes all the velocity corrections, but it's approximate in G. So it's order by order in G. Whereas the post-Newtonian one is really going in this way, so that it's a finite expansion in both velocity and in G, but the product is a certain order, which is measured by this Pn. Yes? Sorry, the diagrams? Infrared or UV? Which one? Both. They are typically infrared divergent because graviton is a massless particle. Massless particles give rise to infrared divergences. But it just means that you have long-range interactions typically, and so you can either have like a cutoff, or you can try to exponentiate your amplitudes, and then the infrared behavior just becomes a phase that you can throw away. So infrared divergences do happen, and they are a problem. I mean, it's a technical problem that requires a lot of extra work, but it's not, it's not. We know what we know what they are. So we're not surprised by them, right? Then the UV divergences, they don't show up in these diagrams that I have here, at least not for the non-spinning case. But eventually, if you go in high enough orders, there will be UV divergences. But they're not due to the quantum nature of gravity. It's just that you have made this point particle approximation to the black hole, and at some point that should break down. And so you have to add corrections for that. So it's just, it's the fact that you're working in an EFT framework for the black hole, and eventually the EFT will break down, and that's a UV divergence. But you should just add it, and then you should match to whatever calculations you can do directly from GR, for example, and then you can, so it's not a problem. Yeah. No, so this is classical physics. No graviton loops. Yeah. It's Feynman diagrams. It looks like loops, but you have to do this carefully, and you have to take a limit where essentially h bar goes to 0. And believe it or not, that does not kill the loops, but it kills the graviton loops. It kills graviton loops, but not loops which involves matter. They're still there. All right. And as you have, Ricardo is the real expert. I'm just pretending to be an expert, so you should ask him. All right. So I put some names here on people who did the first few orders. I guess I already had 1 PN on the previous slide. So here's some higher corrections. And I only went up to 4 PN, probably because when I wrote the talk, most work was done at that order. And okay, here we have Ricardo. I believe people have been chewing away on 5 PN already, but I don't think it's complete. Yeah. Right. So there is some incompleteness in this calculation, but it's on its way. And then people who like to be horizontal, they have computed first up to, up to 3 PM, as indicated here. Also 4 PM, I think essentially by the same people. And there are work even at 5 PM, but I think, again, 5 PM is not complete. Yes, we'll hear about all of it next week. And this is a bit outdated by now, so I apologize to people who were left out. Anyhow, so let's go back to Feynman again. He always has interesting perspectives. And in fact, there was a nice review a few years ago, which I forget what the title was, but it might have been this title, Feynman's perspective on gravity. I forget, you should look it up. But he has very interesting ideas. So his thinking is that gravity, just like an electromagnetism, has quantum foundations, just like I was trying to say before. And general relativity is to be regarded as a classical limit of an underlying quantum theory, whatever it is. And this quantum theory should be investigated by computing physical processes. So he was very keen on computing things which actually is physical rather than computing artificial things, coordinate or whatever. And even if they're not experimentally accessible at a given date, you should still compute them because you will learn something about gravity. And yeah, so the same attitude can be shown with respect to gravitational waves, and that's essentially what I think is going on in community, like the community which has this big overlap between amplitudes people and people doing scattering amplitudes and people doing more traditional GR methods. Okay, so an interesting idea to think about is, what if Einstein would not have discovered gravity, right? What if his geometric approach hadn't happened? Then how would we potentially have discovered gravity, like modern GR, in another way? Well, you can actually discover GR by just thinking about quantum self-consistency. This is well known. So essentially, you can just start by the Newtonian potential, and you can just recognize that that's a massless particle being exchanged. If you know anything about quantum field theory, you see immediately 1/r, that's a massless particle. Therefore, we need to think about which massless particles can mediate gravity. You can go through the list. You start with scalar, then you go to vector, and then you can conclude that both of them should be ruled out. Vectors give repulsive forces, so that does not work. Scalar gives attractive forces, but scalar couples to mass. It doesn't couple to energy. So if you think that energy should be treated the same as mass, then scalars can be ruled out. Next thing after vectors are tensors. So you try a tensor, and then you notice that you can only write down quantum interactions if it's consistent with a symmetry, and this is the famous diffeomorphism symmetry. This is the linearized version. And try to make the symmetry exact by adding nonlinear completion, and this gives a general covariant theory. And in fact, the answer is unique. There is no other choice. GR is the unique lowest derivative theory that respects what I just said here. And in fact, Feynman knew all of this, and he in 1960 did the first Feynman calculation in gravity. He actually did a one-loop quantum gravity calculation, and he noticed that there was something wrong about it. And he noticed that you could fix whatever was wrong if you just added ghost fields. These fields we know as Faddeev-Popov ghosts in the context of Yang-Mills, but he discovered them even before Faddeev-Popov. So which is very, very nice. And in fact, the calculation he did is essentially the same way people calculate today in scattering amplitudes community. You take a process that you understand at tree level, and then you sew it together to get a loop. That's what he did. Okay, so let's look at some Feynman rules for gravity. It's a very interesting exercise. In fact, the first person who wrote them down was Bryce DeWitt in 1967. So after, several years after Feynman had done the calculation, Bryce DeWitt actually wrote down Feynman rules. And there's a whole bunch of them, which I try to indicate here, but let's just look at some of the simplest one. So there's a propagator, usually called the Dondergate propagator. It's not so bad. But then you start going to cubic interactions. This is actually literally copied from DeWitt's paper. And you get this ugly formula, which actually is much worse than it looks like, because it has, actually, when you expand out all this cryptic notation, it's actually 171 terms. Exactly 171. I checked. I counted them. And then you can go to the next order. And I believe I also counted this ones. And that's 2,850 terms at 4 points. And I think that's where he stopped his Feynman rules. Essentially, he was interested in computing. Obviously, he was interested in computing a 4-point amplitude. I believe he even assigned this project to one of his grad students, and that took his whole career, because after he finished the calculation, he left physics. I'm not sure if he actually finished it, but he did leave physics. So, but in these days, we can actually do it very simply using modern methods, which I will get into shortly. But let's look a bit more on how Feynman rules, how the complexity of the Feynman rules grow with the order that you're working at. So if you're just at the propagator level, it's not so bad. It's just 3 terms. But then it starts going bad here. You get 100 terms for the cubic vertex, roughly 100 terms. You get 1,000 terms roughly here, and you get roughly 10,000 terms. So roughly factor 10 each extra order of this vertex expansion. That looks really bad, but the really bad thing's happening when you're multiplying these things, because then it really goes haywire. So if you multiply 2 of these guys, you get 10 to the 4 terms, so 10,000 terms. So see, this is as complicated as this one, right? So this is really bad. Here, 10 to the 7 terms. If you want to try to do loops, 10 to the 10 terms, just naive counting, right? Of course, there's going to be huge cancellation for various reasons, but you don't know which terms are going to cancel against which terms. You have to keep track of all of them before they actually cancel. And it gets really bad if you ever dream about doing 2 loops or 3 loops. So here you reach Avogadro's number of terms. So good luck having that on a computer. By the way, this calculation has been done, but modern methods. There's also a similar calculation for 3 gravitons, which were done much earlier. But this 4 graviton 1 loop calculation has been done, and the people who did it, some of who will be here next week, did not use Feynman diagrams, because then they would never have finished. Okay, so how can I simplify what I just showed you? So it turns out that it's not so hard to simplify gravity if you know roughly what you're doing. And the first thing to look at is to look at weak fields and weakly propagating gravitational waves, or in this case, plane waves. And what you can realize is that you're just describing essentially the quantum fluctuations of a spin 2 particle. But from quantum mechanics, we can always build up higher spin from lower spin, so we can do like a quantum mechanical multiplication. gravitational wave actually factorizes into the polarization tensor of electromagnetic wave in this case. And this factorization actually goes on to higher orders in the perturbative expansion. You just have to know what to look for. And so what you need to look for is you need to look for things which are simple, and that's on-shell processes. On-shell processes are simple, off-shell processes are complicated. So you look at a three-graviton interaction, but you take all the gravitons to be on-shell, meaning that they are not virtual, but they are real, meaning that they satisfy their equation of motion. And when I said they're real, I was really lying. Complex, so never mind. As we have seen in the course that they're actually complex. But the point is that you make sure that they satisfy the equation of motion, and so you have something that you can call like a real graviton propagating, and then you just look at how this interacts, and you notice that no matter what Feynman rules, and no matter how you calculated it on shell, it will always factorize into two factors. Factors being, well, sort of identical copies, and you can recognize them as being the interactions between gauge bosons in Yang-Mills theory. Those of you who don't know, Yang-Mills theory is the theory that describes all of our standard model interactions. So this everybody knows standard model, knows this, how this three-point interaction looks like. Okay, and you can keep on going. You can go to a four-point graviton process, which is basically what I was talking about that DeWitt wanted to do. And then you can actually show that there's an extremely simple formula for it. And it's just going to be the Yang-Mills amplitude at 4 points squared times some kinematic factors which are kind of irrelevant. The point is that all the complexity is in here, and it's not that complex, but yeah, this Yang-Mills amplitude is not so bad, and that also means that this amplitude is really simple. So if only the DeWitt student would have known this formula, could have saved him a lot of pain. Okay, so today we tend to think that gravitational processes are in some sense squared processes of gauge theory ones. So in this case, Yang-Mills. So let's think about Yang-Mills for those who don't know. So Yang-Mills is also one of the more famous frameworks to ever have been written down. And it was written down in 1954 by C.N. Yang and Robert Mills, who are in this picture here. And they were actually trying to describe weak isospin symmetry, which is basically, how neutron and protons can be described by SG2 wave function. So they were trying to describe something which we don't use Yang-Mills for these days very much, but it turned out that they knew what they were doing. They realized that whatever the symmetry, you should look for this symmetry at every point in space-time, and this is what we call local symmetry these days. And by consistency, they could show that there is essentially a unique framework. Just like in the case of GR, you just apply some consistency, and you're led to a unique theory, which is Yang-Mills theory. Well, no, it's not quite unique. It's a term which is called N, which is the number of number of colors these days we call it. What's important is that this color structure of Yang-Mills is very delicately controlled by this mathematical framework of Lie algebras. So we typically use this generators and structure constant that appears in Lie algebras. This also corresponds to interactions in Yang-Mills theory. And as I said today, Yang-Mills theory describes all of the known forces, except for gravity. So the U1, the SG2, and SG3. This is color. This is the electroweak sector. And Specifically, QCD is quantum chromodynamics, which describes how the quarks interact with each other inside the nucleon and proton. Okay, so then I should show this. So this is our modern way of thinking about it, is that we're thinking of Feynman diagrams in Yang-Mills. They're not quite Feynman diagrams, but they're similar enough, so typically we call them Feynman diagrams, but they're not quite. They're cleaned up diagrams often. But we're thinking about diagrams in Yang-Mills theory where the force carrier is the gluon, spin 1 boson of Yang-Mills. And then we think about the prescription which takes us from these interactions to the gravitational interaction. This is what sometimes people call BCA double copy, or there's also a version which is KLT double copy, also another version, some other acronym, but let me not say too much. I also put this here, which is from Quantum Magazine, and I should apologize to David. Where's David? There. I think it was an article about unitarity method, if you remember it, yes. But for some reason, they put a unified physics on the front cover, which actually was referring to how Yang-Mills and gravity is connected. So it's a funny story, but I apologize to David. Yeah, so this double copy gives us a prescription for obtaining gravitational interactions from pure Yang-Mills. But often we not only got GR, but we get extra matter fields, which I'm not sure if I'm going to talk about that anymore, but it's important to note in case it's not exactly GR, but it's close enough. I should also point out that it was known at tree level, coming from string theory. So in some sense, much of the recycling of Yang-Mills amplitudes or gravitational amplitude was already known. But really what we did is that we also understood how to do it and use it at loop level. Okay, good. And also let me point out that here's some of my collaborators, and I guess we got this prize last year, so I figure I should show it. So this is like a new thing that they started giving away. I think they started in 2003 in China. This is Yao's institute, one of his institute. Anyhow, let's move on. So let's try to get a bit dirty and talk more about this double copy. But before we get there, we have to talk about something related, which we call color kinematics duality. And this is really a property about Yang-Mills theory. So let's consider, again, scattering 2 to 2. So 2 gluon goes 2 gluon in, for example, Yang-Mills theory. We know that we can always decompose this amplitude into 3 different channels, ST and U channel. So this is essentially what this notation refers to. There's going to be some color factors which comes from the Lie algebra of Yang-Mills theory, and there's going to be some complicated numerators, which I just schematically indicated by this N here. Well, those of you who know, there might also be some contact interaction, but I have removed them. This is the color factor in terms of Lie algebra structure constants, and here I actually give what these numerators are, just to be concrete. So you can actually line by just sewing together Feynman rules of Yang-Mills, but then you need to add a correction term here. This correction term is essentially just there to reproduce the contact diagram. You can see that this term has an S factor. When you put it here, the S over S will cancel, and therefore this is actually a contact term. Then I should say that it's very important that Yang-Mills has a symmetry that we call gauge symmetry, and this corresponds to an invariance of the amplitude, where we shift the polarization of our amplitudes, and the amplitude remains invariant. This is called gauge invariance, and for this to hold, it's very important that you need these color factors to obey Lie algebra identities. So in particular, it needs to hold it needs to obey what's known as the Jacobi identity. So I've written here in a bit schematic way, but you can essentially figure out that this is just a product of f, so this is just a quadratic equation in the structure constants, just the Jacobi identity. And I stress again, it's very important that these identities exist, otherwise this amplitude can be gauge invariant, right? So you can show that you can derive the fact that Yang-Mills has to live in a Lie algebra, otherwise 4-point amplitudes will not be consistent. Now, what we noticed is that there seemed to be an additional identity that you can apply for this numerator here, and that looks identical to the color Jacobi identity. So we typically call it kinematic Jacobi identity, because it only depends on kinematic building blocks such as momenta and polarizations. And so we didn't really notice it in this context, but we notice it in a slightly more general context where we're looking at some supersymmetric, but never mind. But what we did, when we noticed it, we said, maybe there's some deeper thing going on here. Maybe we should try to always make these kinematic numerators mimic the color factors. Maybe that's a good idea. We tried it for quite some time at the next order, so 5 points, and we keep failing and keep failing. Eventually, we just say, to heck with it, let's just assume it works and then see what the consequence is. So that's what we did, and then we noticed that we got a lot of remarkable output just from assuming that it exists. But that's a story which I guess I didn't have on my slides. But anyhow, so now let's think more about this double copy, because I said the double copy is related to color kinematics duality. So what I just said in the last 3 minutes, should now have some implication for the double copy. So assuming that we have lined up our color Jacobi identity with our kinematic Jacobi identity, then all the identities that these objects and these objects satisfy are the same. So it seems like nothing would go wrong if we just accidentally swapped out color for a numerator for kinematics, color for kinematics replacement. And this is really what's behind the double copy, is that if you do this swap, then if this numerator is the same, what you get is that you get doubled numerators. You get squared numerators. And as I said, you can do this, and it seems like a good idea, but then you check what you got, and remarkably, it's actually an amplitude in general relativity. And you can actually argue that based on general consideration. So you can argue that base numerators contain spin 1 particles. When you square them, they better contain spin 2 particles. You can see it here. You can also argue based on the fact that these numerators came from Yang-Mills interactions, which are one derivative interactions. You can argue that the gravitational interactions better be 2 derivative. And those of you who know your Einstein-Hilbert Lagrangian, you know that every term in that Lagrangian is 2 derivatives. And then finally, based on the fact that you have a gauge symmetry in your gauge theory, this sort of doubles up and becomes the diffeomorphism invariance in this double copy. But it only happens because of this numerator identity. You can show, just in the same way as the the gauge theory, gauge invariance, relies on having a Jacobi identity. You can show that if you do a diffeomorphism transformation on one of your legs, here, for example, particle 4, you can see that you get something which is proportional to this kinematic sum. So only if this sum is 0 will you get something which respects diffeomorphism invariance. And indeed, if you line up color and kinematics, you will get something which is diffeomorphism invariant. Now let me talk about, maybe in the last 10 minutes, let's talk about classical double copies, because there was an interesting development roughly 10 years ago, where people realized that many results in the literature can be reinterpreted as a classical double copy. So in particular, there's a well-known construction of black hole solutions due to Kerr and Schild. This is known as the Kerr-Schild metric ansatz. You essentially identify a null vector in your space-time, and then use that to write down a metric which looks like a perturbative expansion in the sense that you have your flat space and then you have a first order correction to flat space. But it turns out with this k being null, both respect to the full metric and respect to the flat metric at the same time, then this is actually a full solution. It's a full nonlinear solution. And so what people realized, specifically these people here, they realized that this looks a lot similar to how we do double copy at the amplitude level. So maybe there's a connection. So they just thought, yes, let's take this vector here. Let's take this scalar here. This is some potential, scalar potential. This is some vector, which I will show you shortly. You can just multiply them together. You get a gauge field. This gauge field satisfies the equation of motion of E&M, so electromagnetism. So it's a valid solution. And yeah, I'm skipping ahead a bit. Yeah, so essentially what happened here is that the interactions, or so the equations essentially becomes linear. They're not linear, but they look linear. And that's that's one reason why when you do the single copy, they're still linear, and so indeed you know that Maxwell's equations are linear. Anyhow, you can generalize this. You can also do it for, sorry, this is a Schwarzschild metric. Yeah, so here's the explicit solution for this scalar potential, which is just Newton's potential, by the way. And this k vector, well, that's just the radial vector. It's just the radial vector normalized to unity, and then in the time direction, you just put 1. That gives the Schwarzschild metric in Kerr-Schild coordinates or Schwarzschild ansatz form. And then people showed that the single copy here is actually just Coulomb potential. It's Coulomb potential in an unusual gauge, but it's easy to see how to remove this spatial part such that it becomes the standard Coulomb solution. So remarkably, at the level of classical solution, there's actually a map between the Schwarzschild metric and the Coulomb potential, Coulomb solution. And this can be generalized. So this is the known scalar potential for Kerr, the Kerr metric, which is a rotating black hole. And there's a known k vector. I don't actually give the k vector here, but it's essentially the same. It's a k vector, which is the radial vector, not in spherical coordinates, but in spheroidal coordinates. And that's a very important property to use. So this here, r, is actually not a radial distance, but it's a radial distance in spheroidal coordinates, which is not the same thing as in spherical coordinates. But that's too technical for me to elaborate on. The point is that there is a nice solution in Kerr-Schild metric form, and therefore there's also going to be a nice solution for the gauge field. And as far as we know, this gauge theory solution is not known in the literature, maybe because it's slightly weird. It roughly corresponds to a spinning charged disk in E&M. I guess I don't have it here, but I will talk about it later. And maybe I skipped this because it's a bit technical. Oh, maybe I don't. This is actually very important. It turns out that you can actually map between Schwarzschild and Kerr. And this is known, this was discovered by Newman and Janis. So they noticed that when you write your solutions in this Penrose curvature invariant notation, which I'm trying to indicate here, then there's actually a nice shift that you can do. And I'm being a bit schematic, but roughly what's happening is that you can take your Kerr metric in this curvature Newman-Penrose curvature notation, and then you can just say, oh, it's just a complex shift of my Schwarzschild. I'm being a bit schematic here. I'm probably wrong about some details, but roughly that's how it works. You shift your x coordinate in a complex direction with a parameter a. Later on, that a parameter will be the spin of the black hole, or what people call the ring radius of the Schwarzschild black hole. And you can do the same thing for the Coulomb solution. You can just take your Coulomb solution in curvature, in this coordinates. That's also Newman-Penrose coordinates for gauge theory, which is what I'm denoting by phi here. You can just shift it, and then you can get something that is a solution which I think is not known in the literature until it was done in 2014. And so people have, in hindsight, people have called it a root curve. Some people argue that it's related to a charged rotating black hole, but often we don't want to think of it as a black hole solution, but we want to think of it as a gauge theory solution, and therefore we use the name root curve to denote that it's a root of Kerr metric. And there's a corresponding property when you look at 3-point amplitudes. And here I'm not following the standard approach of getting the 3-point amplitudes, but it turns out that 3-point amplitudes for black holes are known, and they take this form where the Kerr 3-point amplitude, so this is one black hole and one graviton, that becomes a 3-point amplitude. And it turns out that it's actually just the Schwarzschild amplitude times an exponential factor, which involves this p dot a. A is the ring radius vector, which is a vector perpendicular to the ring, but it's the length of the ring. And then you can do the same thing for this root Kerr solution, where you start from the Coulomb solution and just multiply it by this exponential, and that gives a 3-point amplitude that we can call root Kerr. And so I have worked on that, but I don't take the blame for the name. The blame for the name is Akane Hamed, Huang, and O'Connell. They're the one who coined root Kerr. And I should say that all of this stuff here, from the amplitudes point of view, was actually understood first in this paper by Alfredo, who's in the audience. Where is he? Or maybe he's not in the audience. He's around, yeah. So this is Alfredo Guevara, Alex Oshirov, and Justin Vines. Okay. Yeah, let's forget about that. Let's skip that. Okay, so I also want to show you some formulas which connects to formulas that we have seen in the school. We might see some of these formulas maybe in the last day of the school as well. So it turns out that you can also formulate these 3-point amplitudes in a more quantum way. So rather than using this classical spin ring radius, so the ring radius is a classical concept. It's not really a quantum thing. But you can translate that into something which looks a lot more quantum, and that's an amplitude for an explicit quantum spin. So here, S here is an integer or a half integer, depending if you want a fermionic state or bosonic state. But the point is that these are quantum spin. And you can actually represent that very nicely in this modern notation that people use this day, which is typically called spinor helicity notation. And it turns out to just be a power. It's just a power of an inner product of two Weil fermions. Chiral fermions. I should say chiral fermions. And so this is the chiral inner product. This is the anti-chiral, vice versa. I don't know which one is which, but so it's extremely simple. That exponential just corresponds to a power. And this amplitude was actually written down by Hamed, Huang, and Huang in 2017. They just wrote it down for accidental reasons. Well, they have some reasons why they thought it was interesting, but of course they had no idea that it was connected to black holes, and that was later discovered by Alfredo Guevara and friends. Yeah, so that's remarkable that they landed on this amplitude, and that seems to be a very good description of the whole amplitude. Now you say, well, what does GR say about this? Well, GR doesn't say much about this process because, first of all, this is happening for complex momenta. So GR doesn't say much about complex anything. GR likes to be real. And so the best thing you can do is you can try to take a soft limit where this leg becomes soft, where the graph becomes soft, and then you can see that yes, this sort of matches the metric or the stress energy tensor which is actually what I'm trying to indicate here. Yeah. So there was work by Justin Vines, where he actually wrote down the stress energy tensor, which is localized, well, at least in his approach, is localized at the point, which I'm not sure if that's quite indicated in this momentum space. It's a bit hard to see in momentum space. But this is a momentum space stress energy tensor, and it also has an exponential form. It's slightly more complicated in this notation, so I'm not going to explain the notation. But the point is that from the stress energy tensor, you can actually show that that matches this amplitude in the limit where the momentum is soft and where the spin is large, and where you have basically classical objects. Then finally, I should also say that there are non-minimal whirlline actions, which also agrees with this amplitude, and that's Levi-Steinhoff work 10 years ago, I guess. Then I guess I'm really running out of time, so let me skip this one, and let me skip this one, and then let me just summarize. So the message of this talk here is that gravitational physics is more important than ever. And that goes back to the 2015 LIGO-Virgo discovery of gravitational waves, but also because of upcoming experiments, LISA, Einstein Telescope, Cosmic Explorer, and of course, everybody who's excited about quantum properties, they're also eager to contribute, think about quantum gravity, black holes, cosmology, and all of those things. Then another message is that, you know, gravity is just a field theory. You know, there's no geometry, it's just field theory. So specifically, it's the quantum field theory of spin 2 particles. And it's the same thing as QED and QCD. It has some problems, which we know of, UV divergences and stuff like that. But you know, it's not much different than these theories if you just think of it as a field theory. And then gravitational waves, they just have the interpretation of coherent states of gravitons. And then the double copy is a nice tool which makes calculations very simple and allows us to recycle Yang-Mills through this slogan here that GR can be thought of as Yang-Mills squared, which goes back to string theory, I should point out. Sometimes I forget to mention that. And the last thing which I was talking about, which I didn't quite finish, but it's this interesting statement that we can actually model black holes using elementary particles, and it actually works surprisingly well, way too well. You know, it's almost a mystery that it works so well. And that also relates to some things that I didn't have time to say, but you can always ask me afterwards. Thank you.
Before opening the floor to questions, we are having a group picture right after the colloquium, before the coffee. So don't rush to coffee. We're having the group picture of the school before the coffee. But now questions and answers.
So how did people think the gravitational force was transmitted if they didn't have gravitational waves?
It didn't have gravitational
waves. How was it transmitted, the force? They knew it wasn't instantaneous, so what did they...
Oh, you mean during this time when people were confused, you mean?
Yeah.
I don't know.
Well,
maybe you can answer it.
It's like the photon, no? You don't need the light to have Coulombic interaction. You can have gravitational Coulombic interaction without the waves. I mean, the Earth is going around the sun, and the gravitational radiation is negligible, but still...
It's not transmitted instantaneously, right?
No, it is, I guess, yeah. I mean, it's Coulombic mode, so instantaneous.
Yeah, I mean, the Coulombic interaction is...
No, but they knew that Einstein knew that it wasn't transmitted instantaneously, right?
Yeah.
So there must be something transmitting it.
Yeah, but you know, the two sectors, the potential sector and the radiative sector are quite distinct phenomenologically. Of course, one cannot stand without the other from the theoretical point of view.
But I guess in the modern language, I mean, there's a difference between off-shell mediation and on-shell mediation, right? And so I guess the on-shell is the gravitational wave, and I guess the off-shell Einstein understood, I guess, yeah. But he also understood the gravitational waves, so he's just, confused.
Yeah, what Weil was saying by mentioning the speed of thought, he was mocking the people that couldn't distinguish the two polarization, the longitudinal and the radiative. And of course, the longitudinal do not propagate with, do not carry away energy, so they can propagate at any speed you like, any speed you may think of, the speed of thought.
So let's go back to Feynman, and
Yep.
and I don't understand in the last conclusion.
Yeah.
What is the observable in black hole scattering?
Well, I think one has to distinguish between actual observables and things which are close to being observables. So, for example, amplitudes. Sometimes you hear the statement that amplitudes are observables, which they're not, of course, but they're very close to being observables because typically what you do is that you compute some cross-section from amplitudes, but you have to make sure that everything you're doing is real. So, for example, in this case, I was talking about 3-point amplitudes, and they're complex. So there's nothing observable about complex momenta, but it's very useful as an analytic tool because we know that the S matrix is an analytic function, so we can explore the whole complex plane. Yeah, so let's come back to so the physical amplitude that people study is a scattering of 2 black holes, right? And so that that's totally physical. You don't see it in experiments yet, but people speculate that maybe in the future, the gravitational wave detectors might be sensitive enough to actually see scattering. And in that sense, you can model that in this amplitudes point of view. And the way you model it is that you assume that the black holes are still well separated, so you don't have to go into the non-perturbative regime. And then everything you can do here from the Feynman diagrams should give a good description of the black hole. But of course, since the black holes are far apart, they are basically point particles, right? The finite size of the black hole plays no role. Then another thing that people start to work on, which I guess I didn't mention, is that if you have a single black hole, you can always send a beam of gravitational waves into the black hole. Well, they don't need to go in, but they can sort of skim off and then comes out again. And this is called, typically people use the word gravitational Compton scattering. And that's not really an observable thing because we don't have a beam of gravitons to send. But in principle, if we had a beam of gravitons, we could make that observation. And this process is actually part of the bigger process because when the black holes are orbiting each other, of course, they're going to send radiation out, and that radiation might skim off the other black hole. So that's a sub-process of the physical process, right? Yeah.
Thank you for the talk. The approach you were showing is for spin 2, let's say, gravitons. But some people in modified gravity also considered vector and scalar gravitational waves. So in what way this could be extended? Like a similar double copy could be designed?
You mean supersymmetric black holes, you mean? Or?
No, it's like modified gravity theories.
Oh, modified gravity.
People will consider possibility of scalar and vector gravitational waves.
Yeah, I think that's fine. I think, at the 3-point level, the interactions are very simple, so you can pretty much include anything. Now you have to just check whether you can do the matching with your theory that you have in mind, right? And the matching is typically done in the limit that the force carrier is soft, right? Because you imagine the black hole momenta is very large, and the momenta of the force carrier is very small, so you take the soft limit, and then you match, and I think there shouldn't be any problem, even if you have some exotic gravity. Yeah, that's fine, yeah.
And the double copy mechanism would work as well?
Yeah, 3-point, everything works. It's almost trivial that it works at 3-point. The real question you have to ask, does it work beyond 3-point? And we do know that it does work beyond 3-point. For example, if you have a Schwarzschild black hole, or if you have a Kerr black hole with very small spin, it works. But at some point, for example, when the spin goes beyond spin 2, then it doesn't work so well at 4-point. Yeah.
Thank you for the talk. Maybe 2 questions. The first one, is there any, Schwarzschild is really interesting, has a very interesting geometry with a horizon, also singularity. Is there an interpretation of this from this double copy side in gauge theory? And also, is this classical double copy really only at the level of the solution, or is there only any statement for some on-shell dynamic, off-shell physics?
Yeah. Well, off-shell is hard to talk about because there you can do anything. But yeah, let's see. What was your first question? I forgot.
Maybe, is there an interpretation of the
the horizon. Yeah, horizon. Yeah. Yeah. So what I was showing was the Kerr-Schild ansatz, and that's sort of a coordinate system which doesn't seem to have a horizon, right? Because there, you don't really see the usual Schwarzschild factors and stuff like that. But of course, you can always do the change of coordinates, and then you go back to standard Schwarzschild coordinates. So that's just a coordinate artifact. I think many people just work in the limit that there is no horizon, because we're so far away from the black hole that you can shrink the horizon to a point. But I do believe that as you systematically include the loop corrections, which are not really quantum corrections, but they're still loop corrections. You still have to do loop integrals. If you systematically include them, then as you go to infinite corrections, the horizon should re-emerge. And people have shown that. I mean, this sort of started with Michael Duff in the 70s. He showed that you can actually solve Einstein's equations perturbatively and resum it to get the Schwarzschild metric. Well, he only showed the first few orders, and then actually recently there was a paper from Copenhagen group which showed that you could actually do it exactly, resum it. So essentially, it's all the nonlinearities, you resum them, and if you're lucky, you get a horizon. Yeah.
So following up to this question, so what does the square root of Kerr solution correspond to? I mean, the square root of Schwarzschild is just the Coulombic potential.
I think physically it's probably just it's just electric charge of Kerr-Newman black hole. That's probably what it is. Yeah. So if you imagine a Kerr-Newman black hole and then you just took the charge distribution, but you forgot about the rest energy distribution, then that's what it is. So it's probably not, as a gauge theory in itself, is probably not consistent, because what is actually supporting this charge distribution, right? It's basically some spinning disk, which is spinning very fast. It has some weird charge distribution, so something has to support that, and I think that's probably not quite physical, right? But we're happy to work with this anyhow, right?
So electromagnetic will be superposition of monopole and some other multiple.
Yeah, I don't know what it is, but I mean, I think people should probably think about more what it could be. Maybe it is something real, maybe, yeah. Yeah.
Okay, I think we can take the last question.
Yes. Hi. Can you get from this techniques, with this techniques, or yes, has anyone been able to get with these techniques any result that you can actually get with any measurable result that you can get with post-Newtonian or post-Minkowskian formalism?
Well, I mean, some of the calculations that I showed you in the PM expansion, they're explicitly done with the double copy, at least the first time they were done. So this is like calculation by Sveburn and friends. These were actually done with the double copy, yeah. And then there was also other calculations by Porto and friends, and I think they were not using double copy, but they were second, right? So the first group who did it was double copy, yeah. Yeah.
And what is the magnitude that is, what is the magnitude, the amplitude?
The magnitude? Yeah.
The observable that you're actually comparing with the post-Newtonian results.
So some of these things that I was talking about was just 2-to-2 scattering, and so in that approximation there was actually no radiation, right? So in order to do radiation, you actually have to do a 5-point calculation, which I had on this slide, which I didn't show you. So this is like radiation at lowest order, 3 level. So basically, you do a 5-point calculation, and you can also match that from the gauge theory to the gravity via a double copy. And there's a whole bunch of work. I think all of them had done this calculation, so yeah.
Okay, thank you.
Okay, stay here for the picture if you're part of the school. And for everybody, let's thank Henrik.